Hey everyone, my name is Tiffany Roberts and this is my Lab 2 presentation. In a nutshell, the purpose of this lab was to observe an object in free-fall motion. This special case is measured using two different methods, one using Tracker to visually observe the motion and create data points across instances of time, and the other using GlowScript to create computational models based on Newton's laws. For this experiment, we needed to use Newton's second law, force equals mass times acceleration, and the position and velocity update equations. It's important to note the main forces we are analyzing are those of gravity and drag. Also, we are observing terminal velocity, in which case there is a net zero force acting on the object, where the force of gravity equals the force of drag, in other words, constant velocity. However, the bulk of this experiment will take place under conditions of non-net zero force, where gravity is accelerating the object downwards. I chose to use two objects in this experiment, the first being a crumpled and flattened piece of paper and a much heavier object, or lacrosse ball, for reference to prove that the flattened piece of paper is actually affected by the drag force. I chose to flatten the paper after crumpling it in order to try to make it fall down as straight as possible. Note that the lacrosse ball has a higher mass and it does hit the ground first. The position, as shown in the graph on the right, is an inverted parabola demonstrating second-order dynamics due to a non-zero net force, and towards the later end of the data, linear dynamics seems to appear, possibly indicating terminal velocity has been reached. I constructed a computer model only taking into account the force of gravity. The arrow shown in the picture in the top left denotes the force of gravity remaining constant throughout the object's motion. In the position versus time graph on the right, we see the same parabolic tendency of the position data from Tracker. In the velocity versus time graph, we see it has a linear tendency from the effect of gravity. Gravity was modeled in the code with force equating to gravity times mass. I also created a computational model taking into account both gravity and drag. The arrow, as in the picture on the top left, gravity is still constant. However, the drag force arrow increases in the upward direction as the object continues falling at higher velocities. However, in the case shown, the drag force arrow is unable to be seen in this scale due to the calculated b value being so small. In the position versus time graph, we still see parabolic tendency. It's difficult to tell if terminal velocity has been reached. In the velocity versus time graph, the velocity is continuously increasing in the negative direction, so we know terminal velocity has not been reached. Had terminal velocity been reached, we would see a perfectly horizontal line. Here is a breakdown of the force equation I used for gravity and drag. The first equation shown was derived by adding the gravity force that is in the negative direction to the positive direction drag force, which is approximated by a drag constant b times the square of the object's velocity. But then what's the value for b? Well, I theorized that when velocity equals terminal velocity, the force of gravity will equal the drag force. Rearranging the equation, we get gravity times mass, which is the weight of the object, equals b times the square of the object's velocity. In this case, v is the terminal velocity that can be approximated by the last two data points of the position versus time graph. We get these values from Tracker data. The value I calculated for velocity was negative 80.45 meters per second. Using this along with a gravitational constant and the object's mass, I found the b value to be 6.821 e negative 6. Here is a results comparison using both the computational prediction models and the observed model. The Tracker data line shown by the blue dots is affected more by drag than the computational models at the later time, but is affected less so from times leading up to 0.3 seconds. This can be attributed to the computational models being based off of a velocity squared relationship. Since the orange line, the gravity and drag data, is slightly higher than the gray gravity data, the model is correct that the drag is slowing the object down, therefore it does not cover as much distance in the negative direction. What does it mean? Can the concept of terminal velocity be seen in the data? Which models of those so far discussed, gravity only or gravity and drag, show evidence of terminal velocity, if any? Well, neither of the velocity versus position graphs exhibit terminal velocity effects, which would have been shown by horizontal lines. However, the observed position versus time graph made using Tracker does show signs that terminal velocity may have been reached, since the line becomes near perfectly straight towards the final moments. Leading into another question, what if? Imagine that the object was initially thrown downward. Would the terminal velocity in this case be the same or different from the case where the same object was initially dropped from rest? Here are the velocity versus time comparisons. The graph on the left shows the original data of the paper ball being dropped from rest. The graph on the right shows altered data having initial velocity set to 10 meters per second. As we can see, the graphs are not obviously dissimilar due to the fact that my calculated b value is so small. However, this trend that should occur is that the graph on the right will turn into a more horizontal slope until it meets the graph on the left at the terminal velocity of the object, thus nullifying the initial 10 meters per second velocity. This concludes my Lab 2 presentation. Thank you for watching.